Yeah, so we're not taking any breaks now. We're continuing directly with the session on non-terrestrial networks, which I'm chairing, so I'm staying here. Before some people leave, let me just also take the opportunity to remind you that there are demos today. The demos are in the rooms one floor below. So if you go out, go down the stairs, there's a room to your left, there's a room to the right. So please, after we finish this session, go and check out the demos as well. All right, so let's move to the next session. So the next session is on non-terrestrial networks. So as you've seen from the roadmap, there was quite some effort that went into this. So we decided to give it a special session. Let me just stay on that. Okay. Just on this one for a second. So we have 3 presentations here. We were supposed to have 4. Frank Zeppenfeld from ESA, who are also supporting this development, were supposed to come, but then they sent their regrets, they're not able to come. So we have 3 presentations. The first one is from Thomas Schlichter from Fraunhofer, so one of our long contributors and long collaborators in OpenAirInterface, and he's going to tell you all the details about the NTN improvements that they did.
Thank you very much, and thank you for skipping it before. Yes, and thank you for staying, because the others that already left will miss very important things. Yes, by the way, there's a slight mistake. I'm not from Fraunhofer HHI, but IIS. I will give a small introduction into Fraunhofer also in the next slide, and you will see Fraunhofer basically is, well, no, let's start first with the title, right? Yes, the title of this talk is OAI 5G and RNTN, physical and MAC layer contributions, because this is basically where we as Fraunhofer IIS are working most. Here we feel comfortable, we do a lot of demonstrations and stuff. But in the end, of course, we use OAI, the end-to-end system. We did also demonstrations, even over real satellites, just as a teaser, with completely 5G and RSA standalone over geostationary satellites. LEO to come, let's say. LEO is difficult. Yes. As said, first I will introduce shortly on Fraunhofer. This is an introduction on Fraunhofer IIS. Maybe a few words up front. Fraunhofer is a complete society of multiple institutes. I think in Germany, or basically it's mostly Germany. I think we are something like 74 institutes, all research institutes, applied research institutes, what basically puts us somewhere between university and industry. And well, we're doing different stuff. Some of the things are slightly overlapping, or where we hopefully, or in the past, already worked together. Like HHI and IIS, we're both very active. For example, in the site link developments, this was really a shared contribution between our institutes, where I'm very proud of that we managed to work together on this. Yes, and here this slide is now about Fraunhofer IIS, so this is one of the institutes. In fact, it's the biggest of the Fraunhofer institutes. It comes from our past, because at IIS, MP3 was invented, and MP3 was kind of a success. So there was quite some money involved, and therefore it was a chance for IIS to grow biggest. But here we're not talking about audio, but our activities in mobile communications. And as you see, we named here different standard entities where we basically actively contribute. We are also contributing to 3GPP since 2015 already on different topics. Satellite is of course one of them, V2X network energy saving just recently, MIMO positioning, RedCap, reduced yes, and other things. Yes, the Fraunhofer IIS itself, it was funded in 1985. We've got more than 1,100, a lot of employees, a lot of budget. The institute itself is so big that it's not only located in indeed one location, but 16 locations, 12 cities, so it's really, really big. The main location is indeed in Erlangen, where I also work. We've got also colleagues working in Nuremberg, mostly on positioning and location. We've got Fürth, Dresden, Ilmenau, and well, a few others. Yes, this is about Fraunhofer. What we at IIS do regarding 5G, 6G is we always try to show it in some kind of circle, because we're active in standardization, we are doing applications, basically proof of concepts, demonstrations, and research. And we do it in a circle because we think the outcome of standardization we usually use in these applications for these demonstrations. And there usually we identify topics that are interesting for research, and then basically the research output is coming back to standardization. So it's some kind of circle. And here in this circle, we've got different projects in the past and currently ongoing. The currently ongoing are highlighted red. You see, well, we've got topics, well, mostly on research and indeed applications. But also on the bottom right, we've got the Fraunhofer onboard processor. So basically there was indeed a satellite launched by DLR, I think, the H2sat, the Heinrich Hertz satellite, and one of the components on board is from us, from Fraunhofer IIS. It's the onboard processor. It's basically a reconfigurable FPGA on board, and there we can do, well, tests directly on board of this satellite. It's a geostationary satellite that is basically always available for tests also. Yes, just recently. Well, I will focus on the projects on the bottom left. The two in black, ESA 5G Goa and 5G LEO, have been finalized in the past. Well, LEO is just in the last days, hopefully, till it's finalized. I will present exactly the outcomes of these two projects. Currently ongoing, just new started, is the 6G LINO. As you see, it's more a 6G project. But there we will indeed build, well, not we, the complete consortium will build a big satellite. I think it's an 8 million satellite. It's a low Earth orbit satellite in this project. Again, with reconfigurable hardware on board. And with this hardware, we want to demonstrate really hopefully the first 5G GNOD B in space. Let's see. Yes, it's quite challenging to be honest. Then the other project is just started is the ESA CV code. It's about NTN, TN demonstration, and V2X applications. So it's basically bringing the things together that we did in the past with OAI. Yes, so now I come to indeed these two projects that I just mentioned, the 5G Goa and the 5G LEO on the next slide, what we as Fraunhofer IIS did. But as you see on the right side, you see the architecture of this project and a lot of companies involved. It was us, of course, Fraunhofer IIS, but also at that time also Eurocom. I think Florian was also involved in this project. We've got University of Luxembourg. We have University of Munich. They were especially for application and the payload, the satellite responsible. And yes, basically in this project, this was where we did the actual 5G NR standalone demonstration over a geostationary satellite. And our contributions from Fraunhofer IIS was the physical layer, the MAC layer, and there were also contributions on the RLC PDCP layer from University of Luxembourg. And we at that time implemented also the Qt-based KPI GUI for OAI. This is just a small overview of the features that we did. I will come up to these features again on the next slides, showing what we merged and what we're currently ongoing on. What we're currently merging. The next slide I said is the 5G LEO project. It's from the architecture, it looks very similar, but there we don't have a low Earth orbit, no geostationary, but a low Earth orbit satellite. But as they are hard to get, we start first in the lab. So it's not an actual 5G, not an actual LEO satellite. It's an emulated satellite in our labs for this sake. But again, 5G NR standalone. As we don't have the real satellite, we don't have the University of Bundeswehr with us. But the other partners, still University of Luxembourg, but Albismart was also contributing a lot to this project, especially on the handover task, because here, the idea is if you've got a LEO satellite, it's moving fast, and we have to hand over between two different satellites. Yes, we had to promise ESA that we would also look into this topic. Yes, therefore, Olbismart at that time implemented within this project the first version of this F1 handover. So basically between two DUs within one CU. We, again, few features on the physical and MAC layer. Again, some updates to the RLC PDCP RC layer by University of Luxembourg. And as said, Olbismart on the handover. Yes, because now I will come to the slide what we actually merged during the project. During the project, we said we will merge back everything that is necessary for NTN, but not limited to NTN. Basically, all these features that you see here were things that we needed for our demonstrations, like PTRS, this phase tracking and reference symbols in PDSH and POSH. The support for 5 megahertz and 15 kilohertz subcarrier spacing. Extended the support for multiple bandwidth parts. We also extended the support for multiple UEs. The implementation at that time of real FDD scheduling, because at that time, before we only had basically TDD scheduling, and we did TDD in 2 different frequency bands and called it FDD. But with this, it was real FDD scheduling. As well, a very first implementation of some kind of QoS scheduling was there also, and some was the implementation of the KPI GUI. But all of these are things that are not specific to NTN. And this is what we said, this we try to merge back directly during the duration of these GUA projects. And this is what we did. So the NTN features, it was more difficult. By the end of the project, we released the code base. So on Eurocom servers, we had basically in the end of the project two branches. One is I don't know it by heart, it's something like NTN 5G GUA, and the other one is NTN 5G LEO. And both of them basically are the completely fully functional implementations that we developed during these projects, but they were based on quite old versions of the develop branch. Therefore, we said just a few months ago, we need to really push these features to the public branch, to the develop branch. And therefore, currently what I'm doing is taking feature by feature from these branches, cleaning them up, polishing them, making them as close as possible compliant to release 17, and pushing them feature by feature to the repository. These are the first things that we actually have in the OAI code by now. I started, of course, with the geostationary satellite simulation. Basically, I extended the RF simulator by the possibility to define this propagation delay, because this is the main impairment from the geostationary satellite, having a much longer propagation channel. So basically, this was the first merge request. Then, of course, to compensate for this, we have to have support on both sides, GNOB and UE side. Therefore, 2 other merge requests. On the GNOB side, we added the support for this cell-specific K-offset, what is introduced by 3GPP in release 17. And on the next merge request, it's basically the UE side, where we use also this cell-specific K-offset and the TA common value. This is basically common timing advance, also being signaled, usually in ZIP19. Regarding ZIP19, I will say a few words later. Yes, then the next thing is, so basically with these 3 merge requests in the beginning, it was possible already to have a complete simulation, and basically also with PropSim, an emulation of an end-to-end geostationary satellite. But to improve the throughput, because we were still using HARC processes, and well, with the 16 HARC processes and this round-trip time of 500 milliseconds, the throughput is extremely limited. Therefore, for this scenario, the 3GPP allowed, or basically specified, that you can disable the feedback. So basically, we call it disable HARC. So we are not using then any retransmissions anymore. The HARC processes are immediately reused. Therefore, basically, we can saturate the downlink and uplink also with larger round-trip times. So this is the next thing, there's immediately reuse uplink, downlink, HARC ID. Yes, then this is basically the core for geostationary satellites. For LEO satellites, we also started. Therefore, what I just found on Florian's presentation was on the GNOB, the LEO support. Maybe this is one of the features that may be ready before the actual deadline in the would be great. I would also be happy, because we started already first with the simulation in RF Simulator. I added support to simulate two of the biggest impairments for LEO satellites. This is the time variant Doppler. So this is changing when the satellite is passing over. Initially it's a very big Doppler, then it's going basically to very shortly zero Doppler, and then going to a very negative Doppler. Similar to delay, very big delay, small delay, big delay again, various, obviously. Yes, these things are being now simulated in RF Simulator. And yes, in the meantime, my colleague also implemented polished and backport or ported forward the support for 32 HARC processes. In release 17, there was an extension from this previously up to 16 HARC processes to now also up to 32 HARC processes in downlink and uplink. Not so important for the geostationary satellites, but for LEO satellites, because the round trip time is something like 40 milliseconds, and 16 HARC processes are there again very little. With 32 HARC processes, you basically can actually use HARC for with LEO. So this extension. Okay, then I'll speed up. Yes, this is the next things that are currently ongoing. As I have the simulation of the Doppler and Doppler and time in RF Simulator. We also contributed already the time, continuous time delay compensation on UE side. This was slightly improved compared to TN. This is now for the frequency offset. So with this it's basically possible then to have the LEO satellite being simulated and emulated with some tweaks. Yes. Next things are more for adaptive modulation coding. SIP19, colleagues from Lasting, that they're going to show a demonstration just now with geostationary satellite and transmission of SIP19, receiving SIP19, using SIP19 for basically all this setting of the delay and all these variables. But this is currently limited to constant values. So basically it's only working for geostationary satellites where the satellite really is not moving. For LEO, we have to update the contents of SIP19. So this is one of the features that we have to contribute. And this makes it more difficult because basically you have to get information about the position of the satellite via an external interface that is unfortunately not standardized in 3GPP. So we have to invent something. Yes, and then NTN UE capabilities. I think that's mostly, I mentioned before the 6G Lino project. I said we want to build up satellites. So this is some information about the 6G Lino project. Just started, very challenging because the time is very small. The budget is relatively small. 8 million is not too much for a real satellite, including the launch. Yes, LEO satellite. Gonna be interesting. I think that's it indeed. So there's my contact slides. I hope I'm having time. Thank you very much.
For the GEO project, the GOA, you mentioned it, the European Space Agency was the partner, and you used their satellite, right?
The satellite that we used, well, I think ESA itself doesn't have satellites. ESA itself is not a satellite operator. To be honest, I don't know exactly which satellite we used at the time. It was a KU-band satellite, I think, a transparent geostationary satellite. I don't know who was actually the operator, because at the time University of Bundeswehr was responsible for acquiring the bandwidth and basically it was thank you very much. It was by SES.
SES? Okay, yes. Luxembourg. Okay.
Thanks, Sumit.
And okay, and I know I have my answer. I mean, for LEO, they are not proposing, SES is not proposing LEO satellite, only Eutelsat and OneWeb.
As I said, for the 6G Lino project, we are going to build our own LEO satellite. Unfortunately, only one, not a complete constellation. This is not within 8 million. It's just one satellite. So we will do LEO tests, hopefully, when the satellite is launched. Yes, with our own payload, basically, yes.
Okay, thanks a lot for everything.
So you're going to put OpenAirInterface in space?
This is indeed what we, yes, the first GNOD B in space might be built on OAI, yes.
Looking forward to that. Okay, and maybe one last question?
What is so challenging?
Uplink.
Uplink. No, especially the timing is only, basically it's only the uplink. In downlink, basically we're syncing and that's it. No, everything, especially the timing advance is exactly the thing. This is why we had this TA common for geostationary, because there it's quite static. Basically it's only for the initial attach, because then we've got the timing advance loop and we follow, we track the. By the way, for real satellites, we indeed did see the satellite is not static, it is moving. And with the timing advance loop, we could even see the changing delay. It was really interesting to see. So this works, obviously. For LEO, it's even more interesting. And there we do something. We basically, it's already in OAI. You can look, maybe even the merge request. There's some documentation. We have some kind of PI controller to predict the timing drift, to basically be able to compensate this as good as possible. Yes, so we predict the timing advance slightly in advance. But still, of course, there's also the timing advance loop for fixing errors.
Well, predict, you compute.
Yeah.
Okay, thank you.
Thanks.
All right, let's thank Thomas again. Thank you.